Welcome to this podcast, in which I would like to introduce calibration procedures for full field strain measurement instruments. The work is based on the VANESSA project, and the presentation has been held on the kick-off meeting of a CEN workshop in Brussels last year. If we talk about the competence of a testing laboratory, there's a standard, the ISO 17025, which defines general requirements for the competence of testing and calibration laboratories. Well, actually, this ISO standard is applicable to all organizations performing measurements, tests and/or calibrations. For example, laboratories where testing and/or calibration performs part of an inspection or product certification. In general, it is said in this standard that the laboratory shall use appropriate procedures for the tests and calibrations that are within the scope of the lab. These include especially an estimation of the measurement uncertainty in these tests. All equipments should be used in a calibrated state before they are put into service. Now, what is calibration? The VIM, the vocabulary defines calibration as the operation that under specified conditions establishes a relation between the quantity values with measurement uncertainties provided on one side by the measurement standard and corresponding indications with associated measurement uncertainties provided by the reference material. If you then have an unbroken chain of comparisons or calibrations, this is used to establish a traceability chain to a primary standard. You're probably familiar with calibration in a single point measurement. For instance, if you are measuring a strain in a tensile test, you expect a homogeneous strain which is determined from two measurements, the elongation delta L and the gauge length L0, and the strain is the ratio of delta L and L0. Now, if you want to establish traceability, you have to calibrate both measuring devices. For instance, that might be a LVDT and the vernier caliper. For the LVDT, you see on the left side a graph that compares the LVDT readings to a laser interferometer reading, and you expect a straight line if they are perfectly collinear. You also see there is slight deviation typical for an LVDT given in the open dots in the graph. On the other side, if you use the vernier caliper, you might use gauge blocks for this step of calibration. What's the difference if you use a camera-based instrument? While for an LVDT, you calibrate a succession of individual points or single values, reference values, except, for example, from this laser interferometer. But for full field measurement techniques, you expect some 10 to the 4 to 10 to the 6 data points. And the question is, how can you do a calibration for such a camera-based method? These include digital image correlation, speckle pattern interferometry, can also be fringe projection or thermal stress analysis. The basic step actually of calibrating a full field instrument is to provide a full field reference value. The comparison should then provide a methodology for comparing such full field data sets from calibration and measurement. We need an uncertainty expression for this comparison step, and we need to establish a traceability chain as well for full field measurement systems. Using reference materials and the methodology for the use is actually a preferred way of calibrating, because there you have an embodiment or a reproduction of full field reference values available. These are two examples. One originates from the SPOTS project and provides a field of strain values in a bending beam, whereas the other one originates from the ADVICE project and is based on a cantilever beam in oscillation, so dynamic, or in static loading. The common feature of both is they are monolithic, and the traceability chain is hooked onto the measurement of a single deformation value, which is V0 on the left for the strain field and W0 on the right for the displacement field of this cantilever beam. So the essential idea is we have a single measurement value that is traced back to the meter, and we have a field of deformation or strain f of x and y, which describes the strain or displacement field in the calibration, in the gauge area. So the left side is a static measurement and provides a static strain field, whereas the cantilever can be run in static loading, but also in a resonant mode of vibration. Both designs are parametric, so you can scale them to the area you need for your calibration, and they are monolithic in a sense that they are machined from a single piece of material. We have a strain map and strain and displacement map given by an analytic expression on, for both materials. The traceability to the meter is through the single value nu0 and W0 on the right. And by having this analytical description of the strain and displacement field, this allows us to extend the traceability to the full field area, to the gauge area of the reference material. These are some experimental results. On the left you have strain field measured by a thermal stress analysis system, and you see a linear evolution of strain from the top to the bottom of this material. On the right you see the deformation of the cantilever in first resonant mode. Again, it's a deformation field from 0 to the maximum deformation at the tip, described by these functions f of x and y. What about the uncertainty values? Now, the uncertainty of the reference values are present because you have manufacturing tolerances, you have an uncertainty when identifying corresponding points on this object, and you have, of course, the uncertainty of your calibration of the single point transducer that you're using for the traceability chain. And these all lead to a material uncertainty, which we call U of Rm, the reference material uncertainty. And then, of course, on the experimental data side, you have the noise in the experiments, but you also have, or might have, some systematic deviations which you'd like to identify by using a calibration procedure. How to compare these full field data? Well, the simplest approach is to use a point-by-point comparison. So you pick a reference value on the locations that are indicated in your camera pixel, and then you plot the deviations of these pairs of comparisons as an area of deviations. You might then use a simple description of these deviation fields, and you get, for instance, a linear field of deviations described by two coefficients alpha and beta. So alpha is more or less a calibration offset that might be present, whereas beta is a calibration bias in your instrument. Having these two coefficients reported allows one to define a unified calibration uncertainty for this process. If you want to decide whether your instrument is acceptable in terms of calibration against the reference material, you can plot the uncertainty of the reference material here in a yellowish shade from the minimum to the maximum reading of your reference values. And if you have a situation where your alpha plus beta x graph, given in green, overlaps this uncertainty of the reference material, you're in a happy position that there is no tangible difference between your measurement system and the reference values of your reference material. Whereas in the red graph, you see there is a substantial deviation between the reference material and the calibration uncertainty. That means this instrument needs to be recalibrated to be used later on in an experiment. Inside the VANESSA project, we have set up an interlaboratory study to use the cantilever material, including a method of loading, a method of achieving different measurements or modes of excitation. The protocol also tells you how to report the measurement data and how to handle and return the reference material. You find this protocol published through the VANESSA website. So when we relate to the Zen Workshop 71 VANESSA, we can say calibration is a special case of validation because it's also a comparison between data sets from experiment and reference values of the reference material in this case. The Zen Workshop is meant to move towards a standard for the validation of computational solid mechanics models using strain field data obtained from calibrated instruments. The Zen Workshop agreement includes both the calibration and validation protocols for optical systems for measuring strain fields and has a protocol for validation using strain field data for computational models. Thank you very much for your attention.